Hi, everybody. Welcome to the CERIAS security seminar. My name is Omar Chaudhry. I'm a postdoc at computer science department here at Purdue. Before I came to Purdue, I was a postdoctoral researcher at Carnegie Mellon University, associated with Scilab. My principal research area, you could say, is like security and privacy, and I use a lot of formal verification techniques like model checking and runtime verification. So I'm going to talk a little bit about checking compliance of computer systems and protocols, and how formal verification techniques can help you achieve this. Okay. So before we go any further, let's try to fix some terminology. So basically, compliance. So I said a word, compliance. So compliance is it's a noun. Okay. And what it basically means is conformity in fulfilling requirements. So what it means is satisfying to some requirement. And the source is it's a Merriam-Webster dictionary. Now, let's try to see how we can use it in a system building and protocol checking scenario. Say you have a system architect who basically builds systems, right? And he's given the job of building a system. So he provides a system design, right? Which is then given to the developers, who basically build the system implementation. Now, every system has some functionality, some requirements that needs to be fulfilled. So there are some requirements, or you could in general say policies that needs to be complied with. So what we want to check is basically whether the system's implementation is compliant with the requirement. Okay, that's at a high level, that's what our goal is. Now, what are the possibilities of why this system implementation is not compliant with the policy? So there could be several reasons, actually. One possibility is like the guy didn't understand, the guy who's responsible for designing the system, he misinterpreted some of the requirements, or he provided a wrong system design, okay? Or the requirement that's given, or the policy it's given, is ambiguous. You can interpret it differently, right? Or the developer misinterpreted while implementing something, right? Or the developer made a mistake. He understood everything, but while coding, he made a mistake. This is very common. Like, developer errors are like everywhere, right? Now, so the thing is, this non-compliance could have a lot of implications. So one possible implication is security or functionality of a system that can be compromised due to non-compliance to the some properties. So nowadays, Internet of Things is very common. Like, you have your thermostat who's smart talking to your mobile phone, your car talking to your mobile phone, right? These are like low-powered devices, and it runs on top of some restricted OS. It's not like a typical OS, but it's just a scaled-down version of it. So Contiki is one example, okay? And Contiki provides, for network communication, some protocols, okay? And these protocols are supposed to satisfy some standard. So for each protocol, it comes with a kind of like a manual, design manual, what it should do. So RFCs are basically, the abbreviation is request for comments. These are kind of standard documents that any protocol should satisfy those. Or your system could have requirement, like because they are low-powered devices, they might have like power issues that you cannot, like those kind of requirements. And so the basic idea is whether these protocols are compliant with these requirements. Okay, that's if this is not compliant, you could have functionality loss, that you cannot, your thermostat cannot talk to your mobile phone, or energy inefficiency. So some of these IoT devices are there for like making a green home. So what it means is the energy efficiency is high. You do not, like, you switch off your AC when you're not at home, switch it on just before you come home, right? That's a typical scenario. Now, if your IoT devices are wasting energy, that's not desirable, right? And then there can be security consequences. So say we take one protocol example, let's say Telnet, okay? It's a very well-known protocol. And say from the system, what you have is a requirement basically said that at a single point of time, the telnet server would support one connection, not more than one connection. If another connection comes while there is an ongoing connection, you should reject it. Now, say you have a client who basically connects to the telnet server, sends a command, right? Before the command can be executed, another client comes in, connects to the server. Say the server is not satisfying this policy and it allows both clients to connect. What could possibly happen is the output could be given to both of them, or half of the output to one guy, half of the output to the other guy. Now, if I'm running a command, I don't want anybody else to see my output, right? And the thing is, like, this is actually a real non-compliance we have discovered during our investigation, right? And we basically ran it through, and it says that half of the result goes to one guy, half of the result goes to the other guy. Okay. Now we're going to talk a little bit about safety implications. Okay. So safety here, I mean physical safety. Okay. Autonomous research vehicles are a big thing now, like Google cars, right? Or Lexus have one. They basically drive around without a driver. They have a human basically riding just for liability issues, but generally the control is totally by the computer. Now, there are safety manuals that is given to them by the car companies, right? And it's required that this car is satisfied the safety manual. For example, I'll give you a very quick example. Like, so cruise control shall disengage for 250 milliseconds within 500 milliseconds of the brake pad being depressed. So what it means is when you brake, right, if your car is in cruise control, it should not be. Okay, that's a safety issue, because why are you braking? You see a car in front of you. That's why you braked, right? So non-compliance can be cause fatality, right? It can cause like loss of life, right? It's serious. Now, let's look at privacy implications of non-compliance. So let's say Homer Simpson is an individual, right? And he basically goes to the hospital. Hospital wants some information from him, his medical history, his personal information, social security. Then there are schools. He goes to school, and school wants some information. Then he opens an account in Google. Google wants some information. And he goes to the bank to open an account. The bank knows some information, right? Let's take a representative organization, say hospital, okay? Now, hospital, like for purposes of medical reasons, right, shares his information with the lab or the health insurance company or the pharmacy, right? These should be allowed. But what's stopping the hospital from selling it in the black market, right? It's a good thing that government has regulations like HIPAA that basically like mandates what can be shared and what cannot be shared. So according to HIPAA, as you have guessed, the first three is allowed, the fourth guy is not allowed, right? So now the question is, what happens if we don't satisfy HIPAA? Now the problem is, if you see the penalties, the size of the penalty, like it incurs civil money penalties. Like organization have to pay a huge amount of penalty, right, for violating HIPAA. Now, and the other thing is like the shame comes with it. Your reputation like goes down. It's like your company, like it's a hospital. It's basically, it cannot protect the patient's information. That's bad. Okay, so it's imperative for the organizations to comply with the applicable regulations. Okay, so my goal is, so far, has been to set up the scenario that checking compliance is important. So I should be kind of convincing you guys that this is an important problem. Okay. Now, how do we check compliance? One very kind of popular way of doing it is test the system. So before you ship it, you test it, right? And there are a lot of disadvantages. Disadvantages are like majority of the testing approaches are manual, right? It's a time-consuming process. It's error-prone. It's incomplete. You don't know whether you've tested all the functionalities, right? And it depends on the quality of the test cases or inputs. If the developer is not good enough, he cannot vision what test cases to test. He cannot like properly test the thing. And in terms of guarantee, it provides very little. So I have tested it. It doesn't tell you anything actually. You can do a bad test, one test case, one very trivial functionality, or very extensive testing. So it doesn't basically tell you a lot in terms of guarantee. So as we have seen that a lot of the requirements can be misunderstood, right? So formal languages can actually help in this regard. So formal languages are well-defined syntax and semantics. So it looks specific. It's not like English. So you can't write arbitrary things. So there are specific things you can write, and they have specific meanings. And what you could do is like expressing these requirements and policies in a formal language enables you to remove ambiguities and misinterpretation. So anybody who can read that language should be able to interpret this without any trouble. There is no like dual interpretation. And the other thing is it also enables us to apply formal verification techniques. So these are like kind of proof techniques like model checking, runtime verification that gives you absolute guarantees, right? And that's why it says like formal verification techniques give you provable guarantees. Testing does not, okay? Now the obvious question is, when do we do compliance checking? So there are different phases you can do compliance checking on. So there are pre-deployment phase is like when you have not deployed the system. So it's just finished writing the implementation. Or in the runtime, it's like the thing is running already, the system is running, you have some safeguard to protect against non-compliance. And finally, there are post-hoc, is like you do it after the fact, right? Now, pre-deployment is basically you take the system, you take the requirement, somehow check compliance before you deploy it. In the runtime phase, you have the system, you basically from the requirement create a monitor, which you can think of a guard, and the monitor basically forbids, like it checks all the action and it forbids non-compliant actions, right? And finally, then you could do post-hoc analysis. Examples are like you capture all the relevant events in a log, which you then check compliance. But note that this is after the fact. So if I collect the log today, I might check compliance a day later. Now the obvious question is, the first two is like pretty satisfactory, right? That means there is no violation. The problem is this last case. Why do we need this? So what is the post-hoc approach going to give us? And where is it applicable? So yeah, so why audit or post-hoc checking? So examples where this is very useful is you don't have enough information during the runtime to make the compliance checking call. You don't know whether an action is compliant or not compliant. And the other possibilities are, it is difficult to weigh in all possible conditions. One possible, like a compliance of an action could depend on a lot of other factors, right? And predominantly the problem is sometimes the relevance, what is a legitimate access depends on the context, like where you are, what time of the day you are. Now, let me try to give you some concrete examples. Hospital, say you have very strict policies, right? And what it basically says is every patient's record can only be accessed through by the doctor of the patient, right? The patient goes to visit a friend in California. He gets sick, gets pulled into the emergency room. Now they have this policy. His doctor is not present there. Now what? The patient should die? Not, right? That doesn't make sense. So in general, in those cases, what they do, they have very relaxed access control, right? They will let you do stuff, but they will check afterwards. And the basic idea is employee wants to keep their job. Even if they get the violation afterwards, they can be fired or hold accountable, right? The other example is speed limits. See? So nowadays, technology has improved a lot. So it would not be very difficult to build a car that basically talks with the speed limit and would not let you go over that. That would be a valid approach of enforcing it. But the problem is there might be cases where you need to go faster than a speed limit. And it's very difficult to understand what those conditions are. You cannot enumerate all of them. So what they do is basically let you drive as fast as you want, but then there is a cop who's basically set a speed trap and waiting for you. Okay. Then next example I have is fraud detection. Like there are fraudulent transactions that happens in banks and financial organizations, right? One of the reasons they are very difficult to differentiate from legitimate access is they look very similar. They look very similar. It's basically, say one guy, say your limit is, fraud limit is 10,000. The guy just basically moves $9,000, but does multiple transactions. So there could be a lot of cases. So in those cases, it's very difficult to detect those on runtime. So what you do is do it afterwards. Okay? Kind of makes sense? Okay. So in this talk, I'll give you three examples. Three pieces of work that I've done with my colleagues here in Purdue and in Carnegie Mellon, where I show examples of compliance checking using formal verification technique in each phase of the system life cycle. Okay? The first is the pre-deployment cycle. So this is a very recent work, and it's called CHIRON. Okay? It's basically checking specification compliance of event-driven network protocol implementations. And it's a joint work with Endadul Haq, Siyu Chow, Christina Nitarataru, and Ning Li. So one of the audience, Endadul, is in this audience today. Okay, so if you have more difficult questions, you can ask him. Okay. So what is the problem statement? So what we basically want is, we want to check implementation of protocols, right? So you're going to be given network stack protocols are often expected to comply with basic requirements, RFCs. I talked about RFCs, right? So, and they have to be compliant. One example is a party must never refuse a request to disable some option. This is a RFC about DHCP. Okay. Now, the problem basically says is, given an event-driven network protocol implementation P, how would one check whether P satisfies some given requirements? We don't like force the requirement to come from RFCs. It can come from anywhere. It could come from the system restrictions or the developer itself. Okay. So what is not our goal? So our goal is finding low-level bugs or memory errors. There are very well-known static analysis tools and techniques that does that. Okay. So we are not doing it. So what we are more interested in is functionality errors. So I'll explain in a bit. So what our high-level approach is basically, so we said these are event-driven protocols. So it's basically what it does is, it sees an event and it has a handler code, and which knows basically how to handle that event. And after seeing that event, it actually the protocol maintains an internal state, and what it does is, after seeing the event, it moves to another state. Okay. So the high-level approach is, we use this technique, very well-known technique called symbolic execution, and we use that to extract a finite state machine, which is basically an abstract functionality of that protocol. And then we use a symbolic model checker to check whether M satisfies the properties written in linear temporal logic. So I talked about formal language, right? So LTL is one example of a formal language. It's a logic basically of time. So what it basically tells you is how different, like the relative ordering of two events in the timeline, whether one happened before the other or like two happened simultaneously. But it doesn't talk about explicit time. It basically talks about relative ordering of events. Okay. And the thing is, the model checker generates a counterexample if a violation is detected. Okay. Now, because of symbolic execution being not complete, what it does, it sometimes gives a spurious counterexample, which basically means is it says there is a violation, actually there is not. This is because of the imprecision of the analysis of symbolic execution, or incompleteness, you can say, not imprecision, incompleteness. Now, what we do is, once we get a counterexample, we have two-state validation process. So first state is we check whether this is actually a logical error. The second is basically we concretely run the protocol with those input and see whether we can see that violation. Okay. So let's see the architecture a little bit better. So on the left-hand side, what it takes is a source of the protocol and two configuration files. So one configuration is protocol specific that the developer needs to give. Another is the network stack it's running on. Okay, and it's fed into the finite state machine extractor. What it outputs is an abstract finite state machine. So what it does then, it's fed into a translator that translates it to a model of the model checker. So it's a language. So it's basically translating from one language to another language. Okay, and from the spec we get the property, the requirements that we saw, like at most one connection at a time. And if there is a counterexample, it would be outputted. What we do is like we parse the counterexample, right? And then what we do is like first step we check whether it's a spurious counterexample. If it is, the spurious checker actually forwards the invariant, which basically tells the model checker, from future investigation, don't like throw this guy out. Never consider this. Okay. If it's a good counterexample, you fed it to the replay counterexample module. What it does is basically run it concretely and see whether that's a valid code path. If that is, then you give it to the visualizer, which visualizes the counterexample. Now, if the model checker basically says the property is valid, then you basically say it's valid. Now, what if we find a counterexample that's not spurious, but when we replay it doesn't like there is no like proper path? In that case, we just throw it out. We basically say this is not a valid one. Okay. So now the obvious question is, why try to do it automatically? So let's say the one on the left, right? You see, this is a specification FSM. It's basically from a textbook, right? The square things are basically states, the arrows are transitions, and there are two parts basically. One before the slash, one after the slash, right? One before the slash is the event that triggers it, and the one after the slash is the protocol takes some action. Okay. Now the thing is, like, people might say this is a small enough protocol, but why can't they look through the code and basically figure out the FSM? Now, one thing we should understand is this FSM is basically kind of an implicit FSM. There are a lot of edges that are missing. So what it basically says is, if I say from state on to state normal, I see an edge basically, if I see a TC any, right, I'll go from state on to state normal. Now, what if the packet is somehow misplaced? It's not a TC any packet, something else. There is a lot of error checking code. Then you should not take the transition, right? You should stay in the state owned. In the code, you have to take those into consideration, whereas you don't have to take those into consideration while drawing this implicit FSM. So the one on the right is basically through our code we extracted. So if you see that the FSM is pretty like complex, right? There is a lot of transitions, and these are basically the hidden transitions I talked about. Especially there is a lot of self loops. It's basically this: if there is an error condition, you don't go somewhere, you stay there, right? So I don't think it's like very easy for a human to do it without making mistakes. Okay. So what is the key idea of FSM extraction? The basic idea is simulate the protocol execution using symbolic execution. We basically run it symbolically, okay, and collect program state information and predicates along the execution path, and map them into the FSM state. Okay, so I'll go into a little bit details. So this is basically how it works. So what it does is there is an event manager that basically tells you what are the possible events I need to handle, right? And then there is an FSM builder whose job is to basically build the system. And a controller is basically the one talks with the symbolic execution engine. Okay, so the first step is basically create the initial FSM state. Then what you do is like get a list of allowed events. Okay, then you the controller prepares the symbolic execution engine to start, and it starts it. And so what it means is step 3. It's basically that the initial state is a FSM state, which could be different than a program state. Program state could have additional variables. So you have to initialize the program state to be like a real program state, not a FSM state. FSM state has less stuff. Program state has more stuff. Okay, and what you do is like you basically give it to the symbolic execution. So you take one event, one FSM state, you give the symbolic execution is basically run. And what happens is it's going to change some state or not change. You basically track that, right? And you basically track that and see that whether every time there is like the symbolic execution stops, whether the state you have right now is a new state. If it's not a new state, you don't worry about it. If it's a new state, you put it in the queue. Okay, and then you add the transition. You do the same for transition. It's basically you see whether there is if this is a transition you have seen before. If yes, you keep it, else you throw it out. And you keep doing it until you don't see anything new anymore. That's basically like a fixed point calculation. Once that is done, you just output the FSM. Okay. Now we developed CHIRON on top of CLI, symbolic execution engine. This is a very kind of common symbolic execution engine. And we checked 5 real implementations, all in C, for two protocols and from 2 different IoT network stacks. And we checked 18 properties, basically, that we collected from different RFCs and the system requirement. And we discovered 10 non-compliances. Okay? And one of the non-compliances I already talked about is allowing both connections, like 2 connections simultaneously. Okay, so any questions so far? Okay, so now I'm going to talk a little bit about checking compliance through runtime verification, okay, or monitoring. What I'm going to do is basically add a monitor that looks at the system's action, each action, and it basically sees whether there is a violation. If there is a violation, it raises a flag. There should be somebody who's going to take care of it. So this is a work with my colleagues at Carnegie Mellon, Aaron Kane, Anupam Datta, and Phil Kufman. So what it does, it's runtime monitoring of an autonomous research vehicle system. So this is actually a prototype of an autonomous research vehicle from an organization that I cannot mention. Okay, so the basic problem is you have a car. So, right? It's basically a system. There are different components, right? They talk to each other through this thing called controller area network, or a CAN bus. It's basically message passing. You pass a message through it. So you basically broadcast. And everybody reads it and basically knows whether the message is for him. Okay? So one of the problems is these are basically black boxes. And they are developed by different providers. So they outsource it a lot like this aerospace industry. A lot of like I saw a talk somewhere. It's basically saying Boeing makes like 13% of the equipment. Everything else is outsourced. So most of them are black boxes, right? You don't know like how they are working. You don't know the code, right? And the system. Now, the other problem is the system has time constraints. Like we looked at, like something has to happen by 250 milliseconds. That's a small time, right? Now, how do we basically protect make sure that the car doesn't do something non-compliant? And as we have seen before, a non-compliant action basically say your car is in cruise control, right? You braked, it didn't stop, and you hit the car in the front. It's catastrophic. You don't want that, right? How can we stop it? So what we do is basically pretty simple. We take the safety manual. We use this metric linear temporal logic. So this is an extension of linear temporal logic with time, because we want to say stuff like within 250 milliseconds something happens. So that logic lets you do it. And from this we basically develop some safety rules in that logic. Okay? And what we do is like synthesize a runtime monitor and a state to proposition map. I'll tell you what that is in a minute. So what it does, it's basically another component, right? It sniffs the bus. So any communication he sniffs. He basically sniffs and checks, right? Now, why is the state to proposition? So the language actually abstracts a lot of information. You just want to know, like, say your policy says speed greater than 60, right? Then something happens. So you just need to know whether the speed is greater than 60. You don't need to know speed is 127 or speed is 80, right? So, but the CAN bus message basically tells you the speed. It basically tells you like 127, 87. So the state to proposition map basically tells you that, oh, the speed is greater than 60. You don't need any other information. You don't need the concrete value, right? And it basically sniffs everything. The other thing it does is these things are continuous. So what it does, rather than like always sniffing, it sniffs every 25 milliseconds. As long as the requirements in your policy are larger than 25 milliseconds, you're good. Okay? Now, in this system, there is a command module actually that on board, which has basically kind of think of, it's kind of like a hard switch. You can switch off the car. Say, very simple example, your brake is half pressed, you're going 120 miles an hour. Something is wrong. So what the command module can do is basically, there is this switch you can take off. And what it happens is, it's basically like a hard switch, your car will come to a stop. Okay? Now, what the monitor does, it basically tells that, oh, there is a violation. And the command module has own rule, it knows what to do. So it does, like, that's not our body. So our goal is to generate this runtime monitor, which basically raises a flag whenever a violation happens. Okay? So overview, so I can't discuss a lot about this paper, so I'm going to go at a very high level. It's basically that we developed a runtime monitoring algorithm that aggressively looks for violation. So one of the things is, in the literature of runtime verification, the policy that talks about future, say it says something like, I do something right now, that means you have to do something 250 milliseconds later. Now, how do I say right now, when I did my action, that the policy is violated or accepted? I can't, because enough time has not passed, right? So the conservative algorithm basically does is, it waits till the 250 milliseconds and then evaluates, basically tells you yes, no. So our algorithm is very aggressive in a sense that it keeps asking, it's like, oh, can I evaluate it right now? Can I evaluate it? So if I cannot, it basically returns an unknown. That means it needs to be evaluated. More information is needed. Okay. So the problem is high computation cost and time. So the onboard computers, they are not very powerful. There are other stuff, right? There is a hardware restriction. Okay. So what we did was, with our initial design, we saw that it's not very helpful. It's taking a lot of power. So what we did was, we basically figured out a way to use both. So try to be aggressive as much as you can. First what you do is do some conservative checking, then you do some aggressive checking, whatever time is left. You do some aggressive checking. So it's basically kind of depends on how your monitoring period, okay? And we evaluated our implementation with by replaying driving logs. So we got a real driving logs for 6 hours and basically ran our system on that. And what we saw is our runtime monitor is actually practical. So it was giving generating errors in proper time. So it was not taking too much time. And we were actually able to satisfy, identify several violations. Okay, several. There is this. So one violation I can talk about is there is this heartbeat message that goes through. It basically tells you that I'm okay, right? And it has to reach some component by some, say, I don't know, 50 milliseconds. If it goes slower than that, or doesn't reach, takes longer than that, it's assumed that component is not working. So we actually found several bugs on that some people were not sending it in timely fashion. Okay, final piece of work. So it's this is also a very new work that got recently accepted. and we want to check compliance through auditing. Okay. So this is a joint work with my colleagues in Max Planck Institute and Carnegie Mellon, and it's what I'm going to talk about is privacy policy audit. I'm not going to talk a lot about equivalence-based security. Okay, so compliance checking of privacy regulations like HIPAA, what happens now? So they have paper disclosure logs. They have privacy laws, which are books. Then you hire a human auditor that comes in every 30 days, basically looks through some records and tells, oh, there is a violation or not, right? Disclosure logs can be pretty long, okay? And it's a manual process, so a human is bound to make mistakes. And this is, as we saw, like a violation can cost you a lot. So you don't want to make mistakes here. So my work has been so far are basically replace the paper with electronic disclosure records, basically save it in a database, okay? And use some logic to replace the policy, okay? And use a semi-automatic compliance checker. So I'll tell you why a little bit, not too much, why a semi-automatic, why not a fully automatic. So some of the regulations that, like HIPAA, basically mention something like you can share some information when the doctor believes it's the right thing to do. How do you model somebody's belief in a computer system? So there are no like systematic way to model beliefs. So what we do is like we speed those out and basically say, I don't know how to evaluate it. Somebody else can evaluate it, right? Possibly a human auditor can evaluate it. That's why it's semi-automatic. So the current problem basically is you have a hospital. It has a log. Now these logs are big, gigabytes and terabytes size. Now you want to, like clouds are very cheap right now. So you want to outsource it to the cloud, right? That's very simple. But audit logs contain sensitive information, patient's information, your proprietary information. You don't want the cloud provider to basically see it. Now what do? It's like you encrypt it, right? But how do you run audit, right? So basically you need to have an approach that allows you to do audit. So one thing I want to say is like one very simplistic way is use fully homomorphic encryption. What it does, it basically lets you do any operation on the encrypted data, but it's prohibitively expensive. It's not practical to use them. And the size of the audit logs are terabyte size. So if you run, like, that's not gonna work. So what our goal is, how can we develop some encryption schemes that basically let you do audit without decrypting anything? Okay, that's the high level goal. So the important research questions are, what operations over encrypted data do we need for auditing? That's the principle. And the second thing is like, we're going to leak some information to do audit. So what is the security guarantees that encryption algorithms give? So for the first question, I'm going to show some examples, and from them I basically show what kind of operations we need. The first is, say, these kind of policies are very common. It's every individual accessing sensitive patient information is in the role of a doctor. Okay, so let's say this is a hypothetical. This is not from HIPAA. This is a hypothetical policy. So you have a sensitive access table, which basically tells that somebody accessed sensitive information and who accessed it. So time of access and who accessed it. That's the sensitive access table. And then there are role table. It basically tells you what each person role is, right? So what you need to do is take a join, right? So, okay, in a more simplistic way, so what we have to do is like, we have to check that, say the first entry is for John. I want to check is John a doctor? That's how I check policies, right? And I have to do it for all entries. So it's okay to take a join, okay? And the next example is, if a patient's medical record is accessed by a billing department employee, then patient must have visited the hospital in the past 1 month, right? Why else do I need to? Because within 30 days they are billed, excuse me. So there is this temporal aspect that something happened before a month ago, right? So you have a patient visit table which tells you different patients' visit time, last visit time, and when you have the medical record access time, who accessed whose record at what time. So it basically means John accessed Alice's record at TJ time, and then you have John is from billing department, right? What you do is like take a join again, right? But the thing is, that's not enough. Say I get this entry, right? I have to say that the time difference between these two are less than 31 days, right? So I have to have a way of checking encrypted times and do comparison, right? So actually what we show that these two operations are enough for auditing HIPAA and GLBA, okay? And so what we need is a join operation and the timestamp comparison. Basically what we need is ET1, ED1 is less than equal to ET2 plus ED2. So T1 and T2 are explicit times, and D1 and D2 are constants, like 30 days, 2 days, or something like this, okay? Now, so what we called our audit log encryption scheme Eunumia. Eunumia is the Greek goddess of societal laws and regulations, okay? And we have two variations of it, okay? So hence the det slash KH. So which one to use when, okay? So deterministic uses, the Eunumia det uses deterministic encryption for checking equality, okay? KH uses keyed hash. It's a specific kind of keyed hash. Eunumia det is less flexible. So once you encrypt the log for a specific policy, then you can't change the policy anymore, okay? Eunumia is more, KH is more flexible. Its policy is not fixed. You can change, okay? The deterministic one has less overhead. The keyed hash has more overhead, okay? And the thing is, like space overhead wise, it's moderate. The EunomiaKH has large space overhead. And deterministic encryptions, the Eunumia det is, the security is proved in the random oracle model, whereas the KH is proved in the standard model. So deterministic, the Eunumia det. So how do we encrypt tables? So what we do is like every column is a single key, okay? Encrypted deterministically. So deterministically means the same IV, okay? Same initialization vector. So if I have the same key, I encrypt John twice, it would be same out ciphertext, okay? So with one restriction, it's like if these two columns are checked for equality, I know that from the policy, then they will be encrypted with the same key. Then I can compare each other, because like John's ciphertext is going to be same, right? It's going to be same. So I can check equality. And the other thing is like times are encrypted with a single key, time fields. So I'm not going to touch into why, because we need to compare times, right? We saw. And there is a data structure that we maintain for comparing time. I'm not going to go into too much details here, okay? So KH basically works, it's pretty simple. It's you encrypt every guy with a single key, right? But whenever you have like two columns need to be compared, you can send a token. What basically this token gives you is like, say you have a keyed hash with key 1, key K2, and with this token, you can actually obtain the keyed hash with key K3. Okay, that's basically K2 to K3. That's the token. Okay, so that's the property. This is a specific keyed hash. It's not like any keyed hash. Okay, so what you could do is like whenever two columns are going to be joined, you basically give the guy the key. Then he can take a join. He can convert one ciphertext, say this K2 to K3. Okay, so let me see. Okay, so I want to point out again, the sensitive access table's name of individual column is encrypted with K2, right? And the name of individual in the role table is encrypted with K3. So these are going to be joined together or checked for equality. What you do is basically send a transfer key. It's called a transfer key. You basically can change keys of the hash, keyed hash. So if, say, okay, so I'll give you a kind of a high-level example. It's like if Bob is, if you take a keyed hash of with K1 with Bob, if with a proper transfer key, you can change it to Bob's K2 key. That's the thing. So contribution overview is like we use guarded first order logic to express the policies. And for comparing times, we use a moped encryption, which we developed. I'm not going to talk about this. And we enhance an existing auditing algorithm from my colleagues, which is called Reduce, for checking to support audit logs encrypted with our scheme. Okay. So our setting is basically whenever a hospital needs like to add something, it adds new events. And whenever you need to encrypt something, audit, you give an encrypted policy and some tokens. The tokens is basically the transfer keys. And the algorithm takes the audit log and these inputs, gives you the encrypted output result. Okay. And the security assurance is that we assume that the privacy policy is publicly known, which is right? HIPAA, everybody knows HIPAA. Anybody can access it. And constant and their encryption are not to the adversary. So I said the policies are encrypted, right? So basically the constants are encrypted. Any constant. If I say like enroll P1 doctor, the doctor is encrypted because that's a constant. And we assume that the table names and their associated column names are known because he's the cloud service provider. He can just go look it up. And our adversary is honest but curious adversary, but it has some extra like additional things. So he can run audit with its choice of audit log. The algorithm is on the cloud. So he can give it an algorithm and a policy and basically run. And the other thing is like he can observe all the interactions. Okay. And our security definition is based on audit log equivalence, and it's basically an indistinguishability kind of definition. So I'll give a high level idea. Okay. So the basic idea is we define a class equivalence class. So if you basically take one guy, encrypt like the log and give it to the adversary. So adversary doesn't know which one from this class he's looking at. Okay, that's the guarantee. However, if the number of logs in that class is 1, if you give it to him, he'll know which log. Okay, so that's the security definition. And for evaluation, what we did was like we evaluated against policies extracted from HIPAA and GLBA. These are real policies. Okay, and implemented both compliance checking algorithm with C++ and generated logs with SQLite, synthetically, and stored it into SQLite databases. For our baseline, which is plain text, our baseline is plain text. For the deterministic one, the overhead is 3 to 9%. This is the time overhead. But for Eunomia, because you need to do this transfer key operation, it goes up to 400%. So it's like 4 times slower. So that's basically for the HIPAA results. If you see like the x-axis is the number of privacy sensitive events that you need to check in the log, and the y is for each guy how long it takes in milliseconds. Okay, so plain, if you see that plain and deterministic are very close most of the time. The keyed hash is has a higher overhead. Okay, for GLVA is the same, or like plain and the deterministic one are very close, but the keyed hash is like it incurs a lot of overhead. So to conclude, it's basically, even though there is a belief that formal verification techniques are very heavy, they cannot be usable, but there are actually, I try to give evidence that there are cases where it can be used. And the thing is like it can be performed in different stages, and deciding which stage to perform compliance checking is basically depends on the application and the restrictions. Okay. So thank you for your attention. So I will take any questions. I don't have a lot of time, I guess. What questions? Yes.
In case of car safety rules, are those safety rules
Please use the mic.
In case of car safety rules, those safety rules are permanent when they are manufacturing?
Is the mic on?
it has to turn green. Yeah.
Where it says push on the bottom, pushing on it.
It's not working.
It's on.
In case of safety rules for cars, are those safety rules hard coded when they manufacture the car, or you can customize those safety rules?
So you can load them up. So the thing is, like, it's not that the monitor is it's oblivious to what policy is enforcing. So you can load it as a policy file. So if you say you have 5 policies now. After testing, you realize you need to kind of import one more policy. You can actually do that. So there is a kind of dedicated memory space which is for loading the memory policies. So it doesn't have to be fixed. Does it answer your question? So it doesn't have to be fixed. So our approach doesn't assume it's fixed, but we were given kind of high-level description, and we basically tested those. Any other questions? Okay, thank you.